All right, let's talk about something that's going to sound completely crazy. You think you're moving through space right now. You're sitting there, maybe you think you're at rest, but you know the Earth is spinning. You know the Earth is going around the sun at about 67,000 miles an hour. The sun is moving through the galaxy. The whole galaxy is moving. So you add it all up, and you think you're flying through space at some enormous speed. But here's what I want to tell you. That's wrong. There's no such thing as moving through space, not in the way you think about it. And the reason why is one of the deepest things in all of physics. Now, this idea goes way back. Newton was the first one to really state it clearly. Newton said, and I'm paraphrasing here, that the motions of bodies in a given space are the same whether that space is at rest uniformly forward in a straight line. Think about what that means for a second. If you're on a spaceship drifting along at a uniform speed, and you do experiments inside that ship, you can't tell you're moving, not by any experiment you can do inside the ship. Your coffee sits still in the cup. You toss a ball up, it comes straight down. Everything behaves exactly as it would if the ship were sitting still. Now you might say, wait, I can look out the window. Sure. Then you see stars going by, and you say, aha, I'm moving. But think about it. The stars are moving relative to you, or you're moving relative to the stars. Which is it? Who's really moving? From your point of view in the ship, you're sitting still, and the stars are streaming past. From the point of view of someone on a star, they're sitting still, and you're going past them. And here's the thing that's hard to accept. Neither one of those points of view is more correct than the other. There's no absolute motion. There's only motion relative to something else. Now, for a long time, people didn't like this. They wanted to believe there was some absolute space, some fixed background, and you could tell how fast you were really moving through it. In the 19th century, when people were studying light, they thought they'd found that absolute space. They thought light was a wave, like sound waves or water waves, and every wave they knew about needed a medium to travel through. Sound needs air. Water waves need water. So they figured light waves must need something too. They called it the ether, this invisible stuff that filled all of space, and light was vibrations in the ether. Now, if there's an ether filling space, then there's an absolute reference frame, the ether's rest frame. And if you're moving through the ether, light should go faster when you're moving with it and slower when you're moving against it. Just like with sound. If you're in a car moving toward a sound source, the sound waves hit you faster. So they did an experiment. Michelson and Morley. Very precise, very clever. They measured the speed of light in different directions at different times of year when the Earth was moving different directions in its orbit. They expected to find differences. They expected to measure the Earth's motion through the ether. They found nothing. The speed of light was the same in every direction, no matter how the Earth was moving. Now, that doesn't make sense with ordinary ideas. How can light go the same speed no matter whether you're moving toward the source or away from it? People tried all kinds of explanations. Maybe the Earth drags the ether along with it. Maybe measuring instruments contract when they move through the ether. All kinds of complicated ideas to save the ether theory. Then Einstein comes along in 1905, and Einstein says something very simple. He says, what if there is no ether? What if light just goes the same speed for everybody, no matter how they're moving? That's it. That's the second postulate of special relativity. The speed of light is the same for all observers. Combined with the first postulate, which is that old principle of relativity, that the laws of physics are the same in all inertial frames. Now, when you accept that light goes the same speed for everybody, something's got to give. Because if I see a light beam, and you're moving relative to me, then by ordinary reasoning you should see that light beam going at a different speed. But you don't. You see it going at the same speed I do. How is that possible? The only way it works is if space and time are not absolute. If different observers have different measurements of space and different measurements of time, when you're moving relative to me, from my point of view, your clocks run slower. Your rulers are contracted. Not because something is physically squashing you, but because space and time themselves depend on your state of motion. This is what the Lorentz transformation tells us. This is the mathematics of special relativity, and it's been tested. We've tested it in every way we can think of. Particles and accelerators live longer when they're moving fast, exactly as relativity predicts. Muons created in the upper atmosphere by cosmic rays, they're moving so fast that their clocks run slow from our point of view, so they make it all the way down to the ground before they decay. GPS satellites have to correct for relativity, or they'd be off by miles. It's not a theory anymore in the sense of being speculative. It's just how the world works. But here's what I really want you to understand. When we say space and time are relative, what we're really saying is that there's no absolute motion through space. You can only talk about motion relative to something else. From your point of view, you can always consider yourself at rest. And that's just as valid as any other point of view. Now you might ask, what about acceleration? Can't I tell if I'm accelerating? Yes, acceleration is different. If that spaceship speeds up, you feel it. You get pushed back in your seat. You can tell you're accelerating without looking outside. But constant velocity, uniform motion in a straight line, no way to tell. That's the content of the principle of relativity. Now, here's something philosophers sometimes get confused about. They hear all motion is relative, and they think that means rotation is relative too. But it's not. Rotation you can detect. If the whole room were rotating, you'd know it. Everybody would get thrown to the walls. Centrifugal effects. The Earth's rotation can be detected with a Foucault pendulum without looking at the stars. So it's not true that all motion is relative. It's only uniform velocity in a straight line that can't be detected without looking outside. The philosopher hears this and gets upset. He says, but wait, maybe we're rotating relative to the stars and nebulae. And he's right. We don't know what would happen if all the stars and nebulae were gone. We've never done that experiment. But the point is, once you admit that even rotation is relative to the nebulae, then it becomes a question that can only be answered by experiment, not by pure thought, not by philosophy, by measurement, by looking at what nature actually does. Now, what does all this mean for how we think about the world? When you look up at the stars, you might think they're so far away. Light takes years to get here from them. And from your point of view, that's true. But here's something wild. From the point of view of a photon, a particle of light, no time passes at all. When you go at the speed of light, time dilation becomes infinite. Your clock stops. From the photon's point of view, it's emitted and absorbed in the same instant. The whole universe is contracted to zero thickness in the direction it's traveling. Every journey is instantaneous from the photon's perspective. Now, is that perspective less real than yours? No, it's just a different reference frame. The universe doesn't have one true perspective. There's no preferred observer, no center, no absolute rest. Just objects in various states of motion relative to each other. And the laws of physics are the same for all of them. That's what we mean by the principle of relativity. And this principle is more than just a nice philosophical idea. It's a constraint on what the laws of physics can be. If I discover a law in my lab, and you're moving at constant velocity relative to me, you have to discover the same law in your lab. Otherwise, we could use the difference to tell who's really moving. So the laws of physics have to have a certain mathematical form. They have to be the same in all inertial frames. This is called covariance. The equations look the same in every reference frame, and that mathematical requirement, that symmetry, has guided us to the correct laws of physics again and again. Einstein used it to find the correct form of the laws of electrodynamics. People use it in quantum field theory. It's one of the most powerful principles we have. Now let me tell you what really happens when you add up all those motions. You're sitting in your chair. You think you're at rest relative to the ground, but the Earth is spinning. So points on the equator are moving about 1,000 miles an hour relative to the Earth's axis. The Earth is going around the Sun at about 67,000 miles an hour. The Sun is orbiting the galaxy at something like 450,000 miles an hour. The galaxy is moving relative to other galaxies. You add it all up, you get some huge number. But that number is meaningless, because every one of those speeds is relative to something else. Relative to the Earth's axis, relative to the Sun, relative to the galactic center. None of them are more true than the statement, I'm sitting still in my chair. From your chair's point of view, you are still. And your chair's point of view is just as valid as any other. That's what we mean when we say there's no absolute motion. So here's what I want you to take away from this. The universe is not a container with things moving through it. Space is not a stage on which physics happens. Space and time are part of what's happening. They're relative. They depend on who's measuring. Motion is always motion relative to something else. Never absolute motion through space itself. And this isn't just some technicality. It's a deep truth about how reality works. Once you really understand this, you start to think about physics differently. You stop asking what's really happening, and you start asking what does each observer measure. You stop looking for absolute truths, and you start looking for relationships, for things that all observers agree on despite measuring different values. Those relationships? Those invariants. Those are what's really real. Like the interval in space-time. Different observers measure different times and different distances, but they all calculate the same space-time interval. That's more fundamental than any individual measurement. This is the lesson of relativity. The world is not what our intuitions tell us. Our intuitions about space and time and motion were formed by experience at low speeds. When we push to high speeds, when we really examine what's going on, we find something different, something more subtle, something more beautiful. A universe where all perspectives are valid, where the laws of physics are the same for everyone, and where the deepest truths are not about individual measurements, but about the relationships between them. And I think that's a pretty wonderful way for the universe to be.